Hello everyone and welcome to the channel. In this video, we'll hook up some extended RAM to our computer and we'll make use for the first time of the extended addressing capabilities of the 65C816. Then we'll take a look at fixing some grounding problems that I'm having and we'll try to improve our Teensy monitor setup. So I hope you enjoy. So in the past video, we've been working on this glue logic module and we've reworked the read and the write pulses so that they take into account all the control signals of the CPU, as well as work within spec for the timings. Now that this is done, I think it's a pretty good base to work with, and I want to go back to adding new features to the CPU. And the next logical step would be to add extended RAM. So we already have built the decoding circuit for the extended RAM address, and in our memory module, we've added the core RAM and the ROM, and it should be pretty easy to now add the extended RAM. So let's do it. So let's take a look at the datasheet of the RAM chip I'm going to use. And that's going to be the Alliance AS6C 4008. So it says here in the datasheets that the AS6C 4008 is a 4 kilobit static random access memory. So that's 512K bytes. And it's going to be an access time of 55 nanoseconds, which is comparable to the other RAM chip that we have. And we'll see later in the timing diagram what it looks like. In terms of functionality, it's completely identical to the RAM chip that we already have. We have some address inputs, some data, in, out, chip enable, a write enable, and an output enable pin. So it's going to be pretty easy to add to our circuit. In terms of characteristics, there's nothing surprising. It's a TTL device, and we'll talk later about the timings. So let's go into KiCad and add the new chip. So thankfully, KiCad already has a built-in symbol for this chip. It's going to need power, ground, and the decoupling capacitor. Then we need to connect the data bus, the address bus, and because we are using inverted bank addresses in our bus, this is now pointing to the inverse of A16, 17, and 18. But for the purpose of the RAM chip, it doesn't actually care whether this is a 0 or 1. And so it's totally fine to invert some of the address bins as long as you always invert them the same way. So now let's connect the control signals. And for the chip select, that's going to be ext RAM chip select. I think I have it in one word. Let's see on the top level. Yes, it's in one word. So we already have this here. Just need to add the label. And we need to add it here as well. Then we can import it. There we go. So in terms of timing, the timing diagrams are going to be almost identical to the existing RAM chip. They seem to be using the same technology, and so the timings are almost the same everywhere. This is the extended RAM in a read cycle. As you can see, we have plenty of margin with our speed. And this is the extended RAM in a write cycle. Again, this is almost identical to the existing chip. So I'm not going to go into detail into how I built this diagram. You can watch one of the previous videos where I add the RAM to see how this was made. But as you can see, we also have plenty of margin with our speed here. Okay, so let's move on to the breadboard and add our new extended RAM. Okay, so this is our computer where we left off the last time. Let's start adding the AS6C 4008 SRAM. And I will be putting it here. So it needs power and ground. And the decoupling capacitor. Now I'm going to cut all the wires to transfer the address bus and the data bus over. I'll do this off camera. Okay, so these are all the wires to connect the existing signals from the first RAM chip to the second. The pinout is identical except for pin number 1, 2, 30, and 31. And so we can just transfer everything over from the existing RAM chip. So let's do that now. So now we can also shorten these wires. The read and the write signal, I can go in here next to the new chip. I'm also going to replace the green wire here, which is a bit too short. Now we need to connect the 4 remaining address pins here. And for that, we can just take them from the bank address over here. 15 goes to pin 31. A16 goes to pin 2. A17 goes to pin 30. And finally, A18 goes to pin 1. There we go. This should be everything. Now we can update our program to not only test the existing RAM chip, but also the new RAM chip we just added. First, let's see if the existing program still works. It looks like it does. Actually, I'm not sure why I'm seeing bank addresses being latched here. Oh, I forgot to connect the chip select of this chip. And that's going to come from pin 6 of the 74AHC32. There we go. Let's try again. Looks like it's working now. Yep. Let's update our program so that it also accesses the new chip. So this is the current program we're executing. We've discussed this in the previous video, so if you haven't seen it, I recommend starting from a couple of videos back and you'll see me code this program. So what it does for now is it loops through the whole addresses that live in the first RAM chip, starting at 7F7F, which is the highest, until 0. And when it reaches 0, it jumps to restart and it starts again. And what it does is it stores 16 bits of data at each address and verifies that it can read it and that it reads the same thing. And if it doesn't, we jump to a fail label, which just put the CPU into the wait state, and this is what we can see in the breadboard. So it's basically just a memory test program to verify that we have hooked it up properly. What we can do to start testing the extended RAM is, instead of jumping to the restart here, we can add a new loop to test the extended RAM. So in order to access the extended RAM, we're going to need to generate addresses outside of bank 0. Specifically, if we look at our memory map, the extended RAM lives in bank 8 to 16. And if we look at the 65C816 programming manual from Western Design Center, in chapter 17, the addressing modes, you can find a diagram for the absolute indexed X addressing that we are currently using for the existing loop. And you can see that we can generate an effective address that contains a bank if we change the data bank register. So it says the data bank register is concatenated with the 16-bit operand, and the 24-bit result is added to X. So in order to access memory in our program, we need to be able to change the data bank register. And the only way to change the data bank register directly is to use the PLB and PHB instructions. So push data bank register onto stack and pull data bank register from stack. So we need to use the stack in order to store the value, and then we need to pull it to the register from the stack. So let's say we want to start at bank 8. We would do STA 8 immediate. Then we would push A onto the stack, and we would pull it to the data bank register. And then we can repeat the same loop. We need to load into X the maximum value of the RAM address within this bank. That's going to be 7FFF. Sorry, that's going to be FFFF, because there's only RAM in this bank. We would align the address to 16 bits. And then we have a second loop that does exactly the same thing. And then when this is done, we need to increment data bank register. And actually, I think I'm going to use the Y register for this. Then I have it here. And when we have reached 16, we know that it's finished. So when the Y register is equal to 16, we know we have reached the end. If it's not, we want to restart, meaning we'll jump to here. And if it is, we will restart the whole program. And I guess this is not a great name. Let me call this loop dbr. Okay, so let's go through this one more time. We first test the bank 0 RAM. When this is done, we continue and we start testing the extended RAM. For this, we use the Y register. The first bank is 8. We push Y onto the stack, and then we pull Y onto the data bank register, effectively changing bank for all data accesses. We load the top of the bank into X, and we align it to 16 bits. We store 16 bits of data at X and X plus 1, verify we read the same thing. If we don't, we jump to fail, then we decrement the address 2 times because we want it aligned to 16 bits, so it's an even number. Until X equals to 0, we repeat this loop, and then we increment the data bank register by incrementing Y. If Y is equal to 16, actually this should be CPY to compare the Y register. If it's not equal, we continue the outer loop. So we push Y to the stack and we pull it into the data bank register. And then if we're equal to 16, we've reached the end and we restart the program. Let me comment the test of the bank 0 RAM, because for this first version, I want to check that the extended RAM works, and then we can compile and program our RAM. This should be LDY. So I'm just not sure this is going to work because this is pushing 16 bits and this is pulling 8 bits. So we might need to do it twice. We'll have to check that. Okay, so let's try it out and we'll see whether it works or not. Okay, so let's try our program. So first opcode is 18, then we have FB, and we set the registers to 16 bits, C2 30. Then we load 8 into the Y register. This is A0, 08, and 00. Then we push Y to the stack. That's opcode 5A. And then we'll see 2 writes at an incrementing address of first 00 and then 08. And then we pull B. So that's AB. And we'll see a read of 08. So the last value that was put on the stack is 08, which is the one that we want to pull into the data bank register. So this code is not going to work because right afterwards we do PLB again. And then here it puts 0 into the data bank register. So that's not going to work. Let me fix that. So it started with the low bytes, then the high bytes, which means that here we are pulling 0 into the data bank register. We need to find another way to decrement the stack pointer by 1. And actually, I think we might need to set the Y register to 8 bits for this operation. That might actually be simpler. There you go. This way here, it's going to be 8 bits. It's going to push only 8 bits to the stack. And this is what we're going to pull into the data bank register. And then for the rest of the code, we go back to 16 bits. And then we need to remember to go back to 8 bits before this part. Okay, so then this should work. So you can see here the LDY is in 8-bit mode. And then here we go back to 16-bit mode. Let's try it out. Okay, so apologies, but my audio and my video froze apparently at this point. But here I am running through the program. Everything seems to be working properly. I set the indexes to 8 bits. Then I go to load Y with 8. This works as well. Then I push Y to the stack. You can see that it does a write of 08 and I pull it into the data bank register. You can see that it will read 8 here. Then I go on to set the indexes back to 16 bits, C2 and then 10. Then I load X with FFFF. This works as well. I decrement it and then I go to transfer X to the A register here. And then I store A at the address pointed by X. And this should generate a bank address. However, as you can see here, the bank address is still 0. So the code is not actually working. It's not generating a bank address. And I'm not sure why, because at the moment this is trying to write in the ROM space. And so, of course, when I try to read back from the ROM, I read EA, which is what the ROM is initialized to. That's normal, but then this makes the program fail. So in order to test that it's actually the program that is not working and not the hardware, I'm just writing a simple test program here that loads a 16-bit value into the accumulator and stores it into RAM at an absolute address that I know is 24 bits. And I'm setting the bank to 8 here so that it actually gets stored into RAM. And then I try to read back from this location again, just to verify that the extended RAM works in the hardware. So let's try this out. So here I am testing the new program, running through the preamble. Then I get here to the load A, ABCD, and then the store A at the absolute 24-bit address. So that's 8F as an opcode, and then it loads the absolute address, and then it writes it to memory. And then as you can see here, we are generating a bank address. So it's not the hardware that is at fault. The latching and the extended RAM works properly, because when I try to read it back again, I can actually get my data back. So this has been written to extended RAM and read back. So the hardware is good, and we have a bug in our program. Okay, so I think I figured out the problem. This is not right. So I'm doing store A to address 0 plus X. But as you can see, this is opcode 95. And if you look at the 65816 programming primer, you can see here that opcode 95 is for the direct page indexed operation. So I'm using the wrong addressing mode. I want the absolute index, which is 9D. And the difference here is whether you give 1 byte or 2 bytes to the instruction. And it's the same actually for the compare right next to it. So the way to fix that is actually to give a 2-byte value. And then this should assemble properly. And it is now using the correct addressing mode that will use the data bank register. So let's try it again. Let me quickly skip through the preamble and get to 90, which is our store A instruction. So it will load 0000, and then it will do right, and you can see here that we are indeed now generating a bank address. So we are writing FE at FFFE and FF at FFFF in bank 8. And then we go to DD, which is the compare, and we are reading again the same data from bank 8. So now the code seems to be working. So let me increase the speed, and it looks like it's working. Okay, so there are a few things I want to improve on the breadboard before we move any further. The first one is I want to take another stab at fixing the signal integrity problems that we have. And for that, it has been recommended to me to increase the grounding distribution on the breadboard. That is, add ground wire when there is connections between breadboards, and we'll do that. The second thing I want to do is I want to improve the speed of the clock connected to the monitor. This is the circuit executing from the monitor right now. And as you can see, it's taking a long while to go through all the banks of memory. It's quite slow. I believe we measured it goes up to, I think, 1 or 1.5 kilohertz. It would be nice to improve that. And then the last thing I want to do is when I'm on the pulse mode, the default state of the pulse is the clock being low. And I have to press the button for data to appear. And it would be nice to change this so that the default state is high, so I can just release the button and see the data appear. So this is what I want to change now. Okay, so we need to improve the grounding of our circuits. Specifically, we need signals going around all breadboards to be followed by a ground wire. This is to reduce the loop area of the signal, and so the inductance. So I already added a ground wire next to the clock here in the last video. I'm going to do something similar for all the inter-breadboard connections here. The read and write pulses are driven by this chip, which is grounded here. So we need to take a ground from here and bring it with them to here. And this chip is grounded here, so we're gonna have the wire go to here. And of course it needs to go close to the signal wires. There we go. The next signal that we have here is actually not really sure which one this is. This is the sync signal, I think. So we also need to add a ground wire here. And this one is being driven by this ground here. And we can go all the way to this ground here. There we go. And I guess this one can also use the same ground wire. It's just a tad too long. I may need to add zip ties to my breadboard at some point for these wires. Then we have those two. And these are going to, one is going to the CPU and the other one is going to the clock. And the ground of the CPU is here. So what we can do is use that same ground wire here and have another wire go here to the ground pin at the top here. There we go. And then this one really needs a ground wire as well. And it's gonna be grounded here at the bottom, so I can just go down to ground here. There we go, that's this one. Then we have the big ones over here. So we have some going this way. And then we can take ground wires for each bundle of 8 wire all the way up to here. And really what I'm doing here is I'm just trying to follow each signal wire as it goes between breadboards and connect it to the ground on the other side. And then let's say we can do one here. I guess I'll do one every 16 wire. There we go, and then we need to ground this here. And then from there, it's going over to here. So what I would really need to do is actually connect the ends here so that the ground has a way to go. And I guess I can do the same here. And these ones I don't care. And I'll do the same here. There we go. And so this should have improved our signal integrity massively. Let's see if we can have it fail really quickly. Looks like it's better. Still getting an error here, but I think this may be programmer error. I don't know. I'm not able to actually get to that point with the monitor connected to see what happens. And this is why I want to improve the speed of the monitor. Okay, so let's go into KiCad and see how we could do that. So the first thing I wanted to do is make sure the input clock stops at a high state when the pulse button is not pressed. And this will allow the data to appear on the bus when I'm not pressing the button. So this will make debugging easier. And I mean, I could go into the clock and, redesign the pulse circuits and the mode selection so that I can make this happen. But I kind of like, as a general clock, that the default state is the clock is off. And so I think what I'm just going to do is invert the output. And so instead of taking the input clock from here, I'm going to take it from the other output. There we go. And now the only thing I need to keep in mind is that the monitor clock also has to be inverted. So this should solve that problem. Now, the next thing is on the monitor side. I want to be able to speed up this code. One thing that this is doing a lot is looping through our pin assignments and reading data using the digital read, and then it's printing one specific bit. The digital read and digital write functions are really slow on the Arduino side. They do a lot of internal bookkeeping and checks that we don't really need. And the outputs of the microcontroller are actually organized into 8-bit ports, which you can actually just access using the port A and port B, etc. variables. And so we could do something like bank address equals to port A. And this will simultaneously read all the 8 bits of the bank address. In order to do that, we have to connect our address bus and our data bus in a way that makes sense in terms of the ports. on the Teensy 2.0 development board, you can see that the ports are actually printed on the silk screen. So let me add this image to our schematic here. And actually let me edit the symbol so that the ports are shown on the symbol. So now the text in the symbol has the microcontroller port, the Arduino port, and then any special function that a pin may have, whether it's connected to the LED, interrupts, PWM, etc. And so now you can see the actual microcontroller ports for each pin. Let's update this. And as you can see, I haven't really paid any attention to this. And so, for example, if you look at the address pins, A0 and A1 are connected to the E port and not in the right order. And then A2, A3, A4, etc. are connected to the D port, also not in the right order. So we have to change the pinout of our Teensy monitor here. So let's do that now. So for the data bus, I'm going to use port C, but I have to reverse all the pins. There we go. Over here, I also have to reverse the order. There we go. Then for the bank address, I can use port B, but I have to pay attention that B7 is over here. So this cannot be the sync signal. And this is port E over here. A23 will have to move here. And then we have to shift everything like this. So I can move VA and sync to those ports here. For the beginning of the address bus, I'm going to use port D, which means that I have to move the monitor clock and read write away from here. And I also have to revert all the pins. Okay, now the monitor clock needs to be on a pin that supports interrupt. So I'm actually going to use one of those. Let's move the sync pin to here. The monitor clock to here, and read write we can move to here. There we go. Let's first start by just updating all the pinouts so I can verify that the new wiring works properly. So one thing I'm noticing here that we are not using, but we should probably wire up properly, is the analog reference pin. And if you look at the data sheet of the microcontroller used in the Teensy 2.0, which is the 8019 USB 1286, if you look at the section for ADC voltage reference, you can see that it says that the external AREF pin is directly connected to the ADC, and the reference voltage can be made more immune to noise by connecting a capacitor between AREF pin and ground. You may not connect a voltage to the AREF pin because it may be shorted depending on the settings you use on the Teensy. And so basically what that says is, depending on how you program the Teensy, there may be a voltage here on this pin. And so connected directly to ground is not good because it's going to short it. So we can't do that. And if you look at the schematic of the Teensy, you can see that on the AREF pin, the decoupling capacitor is already provided. So we can just ignore this pin and disconnect it from ground. There we go. So let's go into the breadboard and make those modifications. Okay, so these two are easy. We just have to flip them. And we have to remove these control lines here. Okay, so let's read write. Goes to pin 11. This one is sync. Now the wire is too short. So these are going to be a bitch. And A23 goes to the other side. There we go. And now we just have to flip this one. Okay, so there's a very high likelihood of something not working here. Let's cross our fingers. Yeah, I put the ROM in the wrong orientation. Okay, so now it seems to be working. Let's see if I have something on the monitor. And yeah, this seems to be working. So I have 1 bit of the address that's not registering. So that's A8, 8, that's pin 31. I have a typo here. Okay, now that's correct. And yeah, this seems to be reading our program correctly. Awesome. The other thing I wanted to do was use the inverted clock of the clock module. So we have to remove this wire here and get the inverted clock, which is over here. So now when I don't press the button, the data bus stays on. That's awesome. And we also have to invert the clock here. And yeah, this is good. Let's measure the clock of the monitor and see where we're at. So I'm going to get the clock from here. Okay, so there's quite a bit of jitter on the clock. That's normal. That's because the Teensy is currently connected to the serial monitor. And so it has to wait for the data to be transmitted and processed by the computer. And this can take varying amounts of time. We're currently at a mean frequency of 1.2 kilohertz. And what's interesting to note is the negative width. So the width of the low pulse of the clock is around 125 nanoseconds. That would be the negative width of the clock at 4 megahertz. And so we are right on the limit for this negative width, but we should be fine. Now let's see what happens if I try to improve this time by using port manipulation. So you can say that the bank is going to be port B. And actually to read the value, we have to use pin B. That's the port input register. And I'm using a tilde to invert it. Remember, the bank address is inverted in our circuit. Then we have the address, the high byte of the address, which is on port F. The low byte of the address, which is on port D. The data, which is on port C. And I really should be using pin everywhere. And finally, the control signals are on pin E. Now, at the moment, we are printing a 1 or a 0 as part of the digital read loop. And this is what gives us the binary output you can see here. Unfortunately, you can't use sprintf on Arduino to print binary strings. So we have to reproduce this somehow. So I will write a function, print byte in binary, which will take a byte. And print it over serial in binary. So we first want to print the bank, then we want the address, and then the data. Then our control signals we can get this way. So VA is connected to pin 7 of port E, read write to port 0, and sync to port 1. And of course we have to give types. Then we can skip the digital reads here, and this should work. So let's verify. Okay, so our Teensy is programmed. Let's see what it looks like on the monitor. Let's reset the CPU. And yeah, it looks like it's working. So I can see bank addresses, I can see writes, opcodes, and my data. Awesome. So what does the speed look like? And so it looks like the speed went to 1.7 kilohertz. So that's not a big change. That's a 40% improvement, but I'm sure we can do much better. Okay, so this was a small improvement in the speed of the monitor clock. Of course, I think we can go much faster. One of the things I'm thinking about doing is having the Teensy send only bytes through the serial connection instead of formatting it into readable characters, and then having a program on the computer that's able to read this stream of bytes and format it on the computer. And this should speed up considerably the speed at which the Teensy is able to transmit data and so rotate the clock. But that's the subject of another episode. I think this one has been long enough. So in the next episode, I think we're going to start adding some I/O. Add a new breadboard here with some peripherals interface adapters, specifically the 65C21. And so the computer is going to be able to input and output data. So that's going to be pretty exciting. So I hope you enjoyed this episode. Let me know in the comments if you've got any questions or feedback. And I hope to see you in the next one. Goodbye.